Hey, welcome back. In this lecture, we're going to be finishing up most of the discussion on closed hashing. There'll be a little bit more in lecture 27, and then most of lecture 27 and all of lecture 28 will be discussing extendable hashing. So where we left off last time, which was 2 minutes ago for me, what we were talking about was the idea of we had talked about this formula where I said this is sort of going to be our index generation formula for our probes, where I say h of x of I, we have here our hash function plus the probing function, and that whole thing will be modulus the table size. And so what we'll then have here when we talk about linear probing, you say f of I equals 1, and so, equals I. And so what we're really getting here is that our offsets will be h of x plus 0 for our first probe. If that's a collision, then try h of x plus 1. If that's a collision, then try h of x plus 2, and so on. Which means then that when we consider the different probing sequences we have, if you initially hash to 0, the sequence you're going to try is 0, 1, 2, 3, 4, 5, and so on. If you initially hash to 1, the sequence you try is 1, 2, 3, 4, 5, 6, and so on. If you initially hash to 2, the sequence you try is 2, then 3 if that's a collision, then 4 if 3 was a collision. If you collide there, 5. If you collide there, 6. If you collide there, 0. And we could do this for all the table cells if we wanted, though I'm only going to do it for one more. But anyway, those would be, actually I can just go ahead and finish these off. 6, 1, 6, 0, 1. So those would be the 7 index probing sequences for the first 4 cells in the table, 0, 1, 2, or 3. Certainly you can have a check in there that says if you do 7 probes in the table, and the table is only size 7, after that point don't even bother anymore. So you can have a check built into your functions there. That's not usually going to be an issue because we won't tend to let our table get completely full, so it won't matter. But you could build a check in there that makes sure you don't try, the 8th probe into your 7-cell table would be back where you started, and you don't want to keep doing that. So you can say, well, if the table is full, then that means I would have done 7 probes in a 7-cell table or 17 probes in a 17-cell table. And if I've done a number of probes equal to the size of the table, then clearly I should stop. And so you could build that into your code and have that be the case. But typically you won't even need the 3rd or 4th cell in the sequence, let alone the 7th or 8th or 9th. We don't, as I said, we don't expect to get many collisions. These sequences are just there in case we need them, because this is how we generate sequences. So the idea then, as we said, was when you insert, you say, well, if I want to insert 9 hashes 2, I keep checking these cells for this 2 probing sequence one by one until I find an empty cell, and I put 9 there. When I do a lookup, I check these cells one by one until I either find 9 or find an empty cell. The problem is that we may have done deletions, which we said last time to ignore for the moment. So what if I had done something like this, where I had said, here's cell 0, 1, 2, 3, 4, 5, and 6. And I had inserted 16, and then I had inserted 11, and then I inserted 9, which collided with 16 but went there. And I inserted 30, which collided with 16 and 9 and 11, and then went there. Let's say I then inserted 13. 13 hashes directly to 6. Then I insert 37, which is going to hash initially to 2, and then we'll try 3, and then 4, and then 5, and then 6, and then 0, and we'll put 37 up there. And then I remove 13, and I say somehow we should remove that from the table. Now, if I run my find procedure looking for 37, the rule we get is we say, well, you try 37's initial value, and then the next value in the sequence, and then the next value in the sequence, and then the next value in the sequence, and you keep trying cells until you either find 37 or hit an empty. And at 6, we hit an empty. That cell is now empty, and so we say, well, that means 37 is not in the table, but it is. Stopping at an empty cell was only a safe thing to do because we didn't do any removes. the explanation for stopping at an empty cell was either 37 would have been here, or we would have inserted 37 after this cell if something else had been here, so that 37 collided with that. There'd be no reason we would have skipped over an empty cell. We would have only skipped over cell 6 if something else had been there already, and since it was empty, we knew nothing else had been there already, and therefore we knew 37 couldn't be further in the table. There would have been no reason to skip over cell 6. Once we allow removals, now we have the ability to say, well, just because it's empty now doesn't mean it was always empty. It could have been empty, could have been filled before, which would have caused 37's insertion to skip over cell 6. And now we've removed 13, so now the cell is empty. But it doesn't mean it was empty before. And so since that seems to now break down this idea of stopping in an empty cell, what's left for us? Well, certainly we could say, I'm going to search over all the cells, but that's going to mean searching is linear time. We don't want that. The whole point of hash tables was to make things as fast as we could. We don't want to search the entire large table. I mean, in real life, the tables will be larger than 7 cells. We don't want to search the entire large table if we don't have to. That's a waste of our, we prefer to do something that wouldn't waste our time to such a degree. And so we don't want to say, well, because there may have been deletions, always search the entire large table for 37. It could be anywhere. It couldn't be anywhere. Or it could be, but we'd better have some better idea of where 37 would be than to say any empty cell could have held something at some time, so search the whole table. Likewise, the solution that sometimes comes to people's minds is to shift the values somewhere, somehow. And this isn't going to be practical. It looks practical on a small table where I say, you know, I could just, when I delete 13, move 37 up there. But that's easy to do because we have a small number of cells and it's easy to see what has to happen. 37 is immediately after cell 6. We could have had a much larger table with legal values, you know, something that hashes to 7 at cell 7, and something that hashes to 8 at cell 8, and something that hashes to 9 at cell 9, and blah, blah, blah. And then down here was 37. Now, do we want to grab 37 and move it all the way up there? Firstly, that involves searching for 37. Secondly, it involves putting 37 at cell 6, and now 37 being missing at that point might cause other problems we need to fix. So somehow trying to replace this, there's a number of strategies you might come up with that all involve somehow shifting values in the table to take that deleted spot into account. They're all going to involve searching and adjusting the table in very nasty ways. And there's a number of things you can come up with, but ultimately whatever you're doing is going to involve, let's see what else could possibly have gone there, and let's put it there, and let's adjust for the effects of moving that other value, and then if we move that, adjust for the effects of moving that. And what it can almost boil down to is to go over every possible probing sequence and verify everything's still okay. There's too many things tied together too much in this table because of the interlacing of different probing sequences and such to make that kind of a move practical, to make searching a table and moving 37 somewhere else, or searching a table for something else that could go in cell 6 and moving it there, it's going to be too much work and it certainly won't be constant time. So deletions could become very expensive. What we effectively have to do is, in a sense, rearrange the entire table, potentially. And we don't want to do that. So what we're going to do, this is the one time where I would think this strategy is acceptable, except in the rarest case. The method we're going to use is one known as lazy deletion. Don't really delete from structure, just mark ignore. That is, what we're going to have is a flag in this cell that will simply mark deleted. Hey, this cell isn't really, you think it holds a value, but it doesn't. Forget about it. Now we're going to need to have that flag in that cell anyway. The reason being that it's easy to see on paper that something is full or not. But in reality, there's no way to do that. I mean, there's going to be some sort of bit pattern even in the quote-unquote empty cells. How do we know what's full and what's empty? We don't. So when actually checking computer code, we will need to have some sort of a flag here that indicates. I'm going to actually draw this on a different piece of paper. we'll have here cell 0, and this will have a flag of E for empty, and cell 1, and this will have a flag of E for empty, and cell 2, this will have a flag of E for empty, and cell 3 will have a flag of E for empty, 4, 5, 6. And so when I put 16 into cell 2, that changes to V for valid, because now I know there's a legitimate value there. And when I insert 11 into cell 4, likewise, that changes to V. And I insert 9, and they say, well, this is a valid cell. It holds 16. That's a collision, so I come down here, and I say, insert 9 into cell 3. Then I wanted to insert the value 30, so I said, well, this is valid, it doesn't contain 30, because we might not want to do duplicates. This is valid and doesn't contain 30. That's valid and doesn't contain 30. This is empty, so I change that to valid and put 30 here. Then when I inserted 13, that hashed directly to 6, changed this to valid and wrote 13 there. Then when I inserted 37, these were all valid. I wrapped around to this point and put 37 up there. Now when I get rid of 13, all I do to do that is I mark this deleted. And what the deleted tag will mean is it'll mean empty for insertion purposes, and it will mean valid, kind of. Find purposes. I say kind of because it's not valid for the actual value 13. What we're saying is we will treat this as a full cell rather than an empty cell and and go past it when doing a search. If I'm looking for 13, I don't really find 13. So it's not really completely valid. We really shouldn't consider it valid. But basically, we will treat it as empty in that if I want to insert a value, go ahead, insert a value and make it valid again. If I want to do a lookup, now when I'm searching for 37, I'll say, well, I don't find it at 2, I don't find it at 3, I don't find it at 4, I don't find it at 5, try 6. And we'll treat that as if it was non-empty. So instead of value, we may think of this as non-empty. Because certainly if I'm looking for 13, I shouldn't say, hey, 13's here, that's a valid cell. It's deleted, 13's not there. But I can sort of view this as, when I say kind of valid, what I mean is it's not empty. So I'll say, okay, I don't find 37 at cell 6, but this was not an empty cell. So I can't stop here. I need to keep searching. Then I try 0 and I find 37. That's the idea of the deleted flag. And this is sometimes called a deleted bit, even though it's not just one bit. But sometimes this is the name given to it, a deleted bit or a delete bit. Anyway, the point is we need this flag anyway to distinguish between valid and empty cells, because even though we can do it easily on paper, there'd be some bit pattern in 1 as well. How do we know what that bit pattern is, whether it's valid or empty? We don't. So we need a flag to tell us whatever bit pattern is in the cell, it's not meaningful, this is an empty cell. And so that flag that could be valid or empty can now also be deleted as well. And that's the idea of lazy deletion. We're not really doing any sort of fancy shifting in the table. What we're saying effectively is to actually delete 13 by way of shifting things around the table to fill in cell 6 somehow is going to be so expensive that it's not worth it. All the strategies you might use on a general large table, a large number of elements, somehow fill that in, and then if you fill that in by stealing a value from somewhere else in the table, filling that spot in, and adjusting for all of this, sometimes it could be quick, sometimes it could be really nasty, so it's not worth it to us. Instead, we're just going to settle for marking this cell, hey, ignore this value, 13 isn't really here. Write over it if you want, and we're simply saying, but it did hold a value at one time. The deleted field is saying this isn't empty, it used to hold value, so you shouldn't stop here when doing a find. You should continue, you should assume that you could have inserted past this cell because this cell used to hold something, And it may have held something at the time you did the insert of whatever it is you're looking for, as it was the case with 37. 13 was legitimately there when we inserted 37. So we don't want to stop at cell 6 when looking for 37. That's the idea of the delete bit, or a lazy deletion. Now, for most structures, you wouldn't want to use lazy deletion. The equivalent on, say, an AVL tree would be, oh, don't really remove a value in an AVL tree. Instead, just find the node and mark it deleted. Ignore it. And so if you expect to have very few removals in an AVL tree, you might say, well, I won't even bother coding up remove, I'll just do lazy deletion. And so I'll just say, when you find the value, mark it ignore, and now you've got maybe in a million cell AVL tree, 3 nodes that are marked ignore, because we didn't expect to do many removals. We've got 3 nodes that are marked ignore this node. And so every time you do a lookup, those 3 nodes are getting in the way and causing perhaps a larger lookup time. But if you only expect a few of those nodes, if you only expect those nodes to be in the way a little bit, then okay, you think it's not going to be too big of a hit. I would still say that the time it takes to do a removal on an AVL tree is not quite so not so bad that it's worth the extra expense you might incur every time you hit those 3 or 4 unneeded nodes. But as far as what lazy deletion would be on some other structure, that would be the idea. We have a 1 million node AVL tree, for example, and instead of, when I want to remove 20, instead of actually removing 20, we just go to the node containing 20 and then mark it as, oh, this is not valid any longer. But it'll mean every time we do a lookup of a node, we have to read the bit and say, is this valid or not, for every node, and then those nodes that are not valid are now going to be in the way when we do a search. And so the time incurred doing all that stuff is likely to be worse than the time you save by not doing those 3 or 4 removals. So it's literally a lazy strategy. You say, oh, I don't want to bother coding remove. I'll just do something, this kind of a hack that says, oh, ignore this node. And I suppose for rapid prototyping, it might be a helpful strategy, but ultimately you're going to want to actually have the actual remove code in place. So I would say lazy deletion, there's exceptions to every rule, but in most situations, lazy deletion is not going to be an appealing use for most structures, because you're going to always have to check, well, is this cell legitimate or not? And that time you take up doing that all the time is going to be just as bad as likely just as bad as the time you may have taken up doing the removal to begin with, or coding the removal. So that's why I said rapid prototyping. If you're just trying to quickly hack up some example structure to show, for some reason, some example, rough coding, you're trying to write a piece of software and you quickly hack up some prototype and say, well, this is kind of how it would work, but a lot of the features are missing. In those kind of situations, it might be acceptable because the whole point was to code things as quickly as you could to get a prototype up and running and then go back and code it right. And so that kind of software engineering method, the rapid prototyping idea, it might be acceptable to use something like lazy deletion or some such. Don't worry about that for this course. I'm just sort of speculating on when it might be useful in other places. As far as our purposes go, the only time it's useful is hashing, simply because the real remove is so expensive that we're better off just using the idea of deletion here, of the delete bit. Now, of course, over time, if you do a lot of deletions, you'll start to have many deletions littering this table. And so what you might end up doing then is you might redefine your load factor to say your load factor is equal to the number of in-use cells divided by number of total cells, where your in-use are cells that are valid or deleted, because those are all cells that would interfere with search. If you have 101 cells, 25 of them are valid, but 75 are marked deleted, there's only one cell that's empty in the whole table, and you're going to stop there as a search, but you'll never stop at any other cell when doing a search. So certainly that's going to affect your performance for find, because every find potentially looks over almost the entire table. And so as you start to have a lot of deleted cells littering your table, that might be unappealing to you. So even though you might not have many elements in the table, the fact that there's a lot of deleted cells could be a bad thing. And so your load factor might be based on that. Should be based on the number of valid and deleted cells. And so when it comes time to increase the size of the table, or at the very least, simply rehash everything into a fresh table of that size, then that would be the trigger for that. You'd say, when my load factor O is more than 50%, we'll say. If your table is more than half full, that might mean when you have more than half the cells are valid, or a better way to do it might be to say when more than half the cells are valid or deleted, now fewer than half are empty. And so at this point I should now either increase the size of the table, or if most of the trouble is due to deleted cells, I could perhaps keep the table the same size and simply rehash everything into a fresh table of that size, rather than a fresh table that's larger. So anyway, the point is, yeah, these deleted cells can get in the way, but it's still more appealing to us than having to restructure the entire table with every remove, because for the most part, we don't expect too much of a problem. So anyway, that's the idea of closed hashing. What we expect here is, as before, we really don't expect many collisions, so I expect constant time average case for insert. I expect to be able to insert quickly. I expect to be able to therefore look down that sequence quickly, and then remove is simply going to be to do a find and then mark that cell deleted. And so we expect average case for all of those. In the worst case, as the table starts to fill up, or if we have a really bizarre sequence of insert, that everything hashes to 2 or whatever, then again we expect order n for all 3. And this will be true regardless of the kind of probing we're using. We're going to look at different probing strategies next. But regardless of the particular probing strategy we're using, this will indeed be the case. That our average case is going to be constant time for the 3 operations, and the worst case will be linear time. And that's going to be what hashing is. We'll try to keep the table size larger so that we can hit this average case. We're more likely to hit that average case. So that's, in a sense, what we're doing. We're trading memory for time. With a larger hash table, the constant time becomes more likely. If we let the table get too full, if we let that load factor climb close to 1, instead of perhaps increasing the table when the load factor is 25% or 50%, when it's a fourth or a half full or something like that. In that case, then if the load factor is kept limited, then the table size is larger, and we should have more room in the table and tend to get the constant performance. As the table starts to fill up, we're going to have linear performance. So even though the linear probing that we've looked at does indeed support a completely full table, it'll work if we let our table get almost full, or obviously we can't insert if the table is totally full. But the idea is we could go up to totally full, and linear probing would still work technically, but it would be a bad running time. You'd expect to be doing a certain number of collisions, and everything would require looking at every cell. It'd be a pain. So we probably want to have the table be much less than 100% filled. And we'll talk about that a little bit more at the beginning of next lecture. So the only other thing to talk about is different probing strategies. And we have different options for probing. Linear probing is one of those options. We said that we can say that the probing function f of I is equal to I, and because it's equal to I, we then get the ability to, basically we're going down cell by cell in the table as we do our lookup. Now, when we deal with different probing strategies, what we're going to be doing is changing the f of I value. And that's going to be how this works. F of I equals something else. And so instead of having a sequence that just goes down the table cell by cell and says, okay, our sequence is 2 and then 3 and then 4 and then 5, we will do different kinds of probings, different sequences where we're jumping to different places in the table. And the question is, why would we bother? And the answer is, well, linear probing has some disadvantages, or it has a big disadvantage. And that disadvantage is something known as primary clustering. Because of the way linear probing works, we have firstly these severe overlap. This makes it even worse. The severe overlap of probing sequences, which means that any later collision I have in the probing sequence for things that start at 2 is also messing, interfering with the early parts of the probing sequence for 3 or 4. But when we try and solve our collisions, let's say I happen to have now 2 values that are next to each other. If I hash to either of these 2 values, what I'm going to do is keep traversing downward until I find a free cell. So if I hash to this second cell, I'm going to add down here. If I hash to this first cell, I'll collide also with the second cell, and I'll add down here. Now I have 3 cells clustered together. If I hash to any one of them, I'm going to collide with everything below it. That is, I have 3 cells. If I hash to the top one, I'll collide there. I'll also collide with the second and third cells. If I hash to the second one, I'll also collide with the third one. If I hash the third one, then I just collide with that. But the idea is, when I have these clustered together, because of how linear probing works, it just has you look at the cells downward one by one. If you hash to any spot in a cluster, you're going to collide not just with that value, but everything below it in the cluster down to the bottom, and then you're going to add to that cluster by adding to the next empty cell underneath it, making it worse. Now that cluster is a larger target. You're more likely to hash into something that collide with something in that cluster with your hash. And when you do, you're now going to have to collide with everything else as you go down, making it yet a larger target, making you more likely to hash into that target somewhere, and then you have to have a bunch of collisions until you reach your next cell on the bottom, and so on and so forth. So this is the problem you run into. This is called primary clustering, the idea of having these large clusters that build, that as they get larger, you become more likely to hit them when you hash to some random cell. And when you do hit them, you collide with every cell from where you entered down to the bottom of the cluster. And this becomes even worse if you happen to have, another cluster down here somewhere. As you add cells to this cluster, you're eventually going to hit that one, and now the two of them merge, and the next thing you insert has to go down to the bottom of the entire joined cluster. So the clustering effect with linear probing is very, very bad. What we'd like instead is to say that when I hash into this cluster somewhere, the next spot I try is somewhere entirely different in the table. That way I can have a large cluster. Big deal. If I have a large cluster, my first attempt will collide with that cluster. My second attempt goes somewhere entirely different in the table. If that were the case, then the clustering wouldn't matter, this primary clustering effect. But since linear probing says try every cell in sequence one by one, starting from where you began, then if you hit a cluster, you're doomed to hit every value in that cluster. That's a bad effect of linear probing that we'd like to avoid. So, one possibility for avoiding it is to say, well, we can use quadratic probing. The idea here is f of I equals I squared. In other words, our probing function is quadratic. So when we have our sort of overall attempt here, we say x comma I equals h of x plus f of I, whole thing mod the table size. What we're really saying here is that's going to equal h of x plus I squared, the entire thing mod the table size. Now notice as before, f of 0 equals 0. That's what we want. So the first probe will actually be to the hash spot. And then what we're going to try progressively is, well, after trying h of x plus 0, which we always want to do, we'll then try h of x plus 1. And if that is a collision as well, we'll try h of x plus 4. And if that's a collision as well, we'll try h of x plus 9. And if that's a collision as well, we'll try h of x plus 16. And if that's a collision as well, we'll try h of x plus 25. So these, of course, as before, are all mod size. So eventually we wrap around the table. So instead of adding as offsets 0 and then 1 and then 2 and then 3 and then 4 and then 5 from the initial location, instead we're adding the squares of those numbers. We're adding as offsets to the initial location 0 and then 1 and then 4 and then 9 and then 16 and then 25 and so on. That's the only difference. When we change probing strategies, the algorithms don't change. We have a probing sequence generated by the probing strategy, and we still say to insert, we follow the probing sequence cell by cell until we find an empty spot, put our value there. To do lookups, you follow the probing sequence cell by cell until you either find your value or you hit an empty cell. Not a deleted, but an empty cell. And to do deletion, you do a lookup, find your value, and then mark the flag delete. That procedure for insert, find, and remove works the same way no matter what probing strategy we use. The only difference with what we're doing here is we're generating different probing sequences now. But once you have a probing sequence, some collection of cells to try, the first cell to try, the second cell to try, the third cell to try for a particular X. Once you have the probing sequence, everything works the same way. The rules of closed hashing work how we've discussed. Insert works the way we've discussed, find works the way we've discussed, delete works the way we've discussed. Don't get tangled up on that. Remember the rules for insert, find, and delete. Once you've done that, the only question is what cells do you try in what order? When trying to insert a value into the table, which cells do I try in what order? When trying to look up a cell in the table, which cells do I look up in what order before I find an empty cell and stop? When trying to remove, what cells do I look up in what order before I either find my cell or hit an empty? Everything depends on the sequence of cells we want, the probing sequence. So we've basically, in describing insert, remove, and find, we've described in terms of the probing sequence. The particular example we used was a linear probing sequence. But if we change that to a different kind of probing sequence, don't think that, and it's a point of confusion sometimes for people, don't think it changes anything we've talked about as far as the operations. All we're changing is the particular set of cells we look at in the order we look at them. That said, by way of an example here, if your h of x was 2, if you had linear probing, this would have been your sequence for a size 7 table. Let me just do this. For whatever the size of your table was, that would be your linear probing sequence. For quadratic probing, this would be your sequence. 2, 2 plus 1, 2 plus 4, 2 plus 9, 2 plus 16, 2 plus 25, 2 plus 36, 2 plus 49, and so on. So those are the cells you're going to try. For linear probing, given a large table, you would try 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and so on. For a, go ahead and write that. For a quadratic probing table, you're going to try 2, and then 3, and then 6, and 11, and 18, and 27, and so on. Now, the effects won't be terribly noticeable on our small example. They'll be more noticeable on a large table size. But basically, if I was to quickly sketch out a few large tables without doing much detail, for linear probing, these would be the cells you would try one by one. And for quadratic probing, you're going to end up instead saying, I'll try this cell, then this one, then this one, then this one, and then that one down there, and then that one. So while we're stuck trying consecutive cells there, these would be the cells we might try for quadratic probing. And you can see they're far more spaced out around the table, which is good for us. So that'll be the idea. Each probe is further and further away from the last one. It doesn't exactly show well in that picture, but anyway. By way of a real example, if I actually want to write cells into the table, oops, just dropped the microphone. Dropped the microphone, sorry. So we say here, zero, 1, 2, 3, 4, 5, and 6. I want to insert, say, 16. That hashes to 2. I want to insert 9. That also hashes to 2. I collide with 2, so I try cell 3 next. I want to insert 30. That also hashes to 2. I collide with 2. I collide with 3. I'll try 6 next. And so I put 30 there. I want to insert 2. That also hashes to 2. I collide with 2. I collide with 3. I collide with 6. Next I want to try 11. 11 mod 7 is 4, and so I wrap around and insert in cell 4, and that's where 2 would go. So yeah, it starts to get cluttered anyway because we've got such a small table. But the idea would be, normally we'd have 2, 3, 6, and 11 would be where these values would go. Instead now, because I have a small table, it's 2, 3, 6, and then 11 wraps around to 4, but that's how it goes. So that's an example of quadratic probing. Instead of inserting them in 16, 9, 30, and 2, which would have been how I did linear probing, I had 16, 9 was 1 away from the initial cell, 30 was 4 away, not 2 away from the initial cell, and 2 was 9 away, not 3 away from the initial cell. And in practice, because the table is so small, it ended up being only 2 away anyway. But anyway, with a larger table, 2 would be somewhere down here, and it would be 9 away from cell 2, not 3 away, as you would have had with linear probing. There's not really a whole lot more to say about how this works. We've got a different probing sequence. When we insert the values, they end up in different cells. That's really all there is to it. The inserts work the same way. Lookup works the same way. If I'm looking for 37 now, I will try cell 2, and then cell 3, and then cell 6, and then cell 11, which is cell 4, and then cell 18, which is also cell 4. And here we start to get an interesting effect. If I'm looking for 37, when do I hit that empty cell? Better yet, if I'm trying to insert 37, when do I hit that empty cell that I can insert into it? We need that empty cell to know 37 is not in the table. We also need that empty cell if I want to put 37 in the table. And note something interesting. Following this probing sequence, 18 is cell 4. That's taken. 27 mod 7 is 6. That's taken. 38 mod 7 is 3. That's taken. 51 mod 7 is 2. That's taken. The next cell would be 68, 64 plus 2. 68 mod 7 is going to be, that can't be, no, 66, I'm sorry. 66 is 64 plus 2. That 66 mod 7 is 3. That's taken. The next cell would be 81 plus 2. That's 83. 83 mod 7 is going to be 6. That's taken. And we keep hitting these same values over and over again. 2, 3, 4, and 6. And in fact, we're going to keep doing that. It's going to be impossible to insert 37 into this table. We'll never find an empty cell, even though there are 3 empty cells there. And as a result, if we're trying to confirm that 37 is or isn't here, well, we're never going to hit that empty cell to tell us to stop searching either. Quadratic probing has a problem, which is that once the table is more than half full, we're stuck. And for doing probes, for looking up 37, we could at least say, well, once you've done 7 probes, the table size is 7, you know you should stop. But for insertion, we're going to want to put 37 in there. So even if we bounce around the same 4 cells for a while when looking for 37, eventually we can say we've done too many probes. You know, we've done 7 probes already. Clearly, we would have had a chance to look at every cell on the table if we could. So forget it. We're done. 37's not here. But if we're trying to insert 37, we don't want to stop early. We want to actually insert 37 into the table, and we're going to have that problem here. We're going to bounce around the same 4 cells. We're never going to find an empty cell to put 37 into. This is a peculiar effect of the mathematics of tables and quadratic probing. It so happens that given your table size, you can get these loops of cells that take up just over half the table. So if your table size is 7, these sort of loops consist of 4 values. If the table size is 17, the loops would consist of 9 values. But the idea then is, once those values are all used up, for a given table size and for a given starting location, your quadratic probing is only going to be able to use 4 of those cells. That is, your 5th hash into a quadratic probing table is going to collide with one of the previous 4 cells, if the size is 7. Your 6th hash, your 6th probe, is going to collide with one of the first 4 cells. Your 7th probe will collide with one of the first 4 cells. Your 8th probe will collide with one of the first 4 cells in this sequence. So really, the only part of the sequence that's of any use to us is going to be the first 4 cells in the size 7 table. Given this table size, just over half the table size, those are going to be the only number of cells that will be of use to us. Now, if I'm going to insert, say, 5 or 12 that hash to 5, that's empty. I can put that there. Likewise, like the cell 1, for example, if I start at 1, the cells I'm talking about that are part of this effect would be 1, 2, 5, and 3. 1, 1 plus 1, 1 plus 4, and 1 plus 9 is 10, which mod 7 is 3. Once 1, 2, 5, and 3 are filled up, I won't be able to hash anything that hashes to 1. I'll keep colliding with those 4 values. Or in other words, the rule for quadratic probing is quadratic probing can't guarantee an insertion will work once table is greater than 1/2 full. And so as a result, we don't want a quadratic hash table be more than 50% full. So for something like linear probing, even though we said performance would degrade as it gets full, we could let it get 100% full. Quadratic probing specifically, we don't want it to get more than 50% full because the insertion is no longer guaranteed to work once it's more than half full. You can get that sort of weird numeric effect we just saw, and the result of that will then be that, if all, for a table size of 7, if the first 4 cells in the sequence are taken up, you won't be able to, all the other cells will hash the same as the first cells in the sequence. If you have a table size of 17, the first 9 cells in the probing sequence are legitimate, and then the 10th, 11th, 12th, 13th, and so on, the later cells in the probing sequence, the table size would just be duplicates of the earlier cells. Where something like linear probing will actually give you 1 by 1 every cell in the table. Quadratic probing won't. The next method we look at will also 1 by 1 give you every cell in the table. Quadratic probing, the idea that it won't is an effect of quadratic probing. And so that's the downside here. We avoid the primary clustering problem, but we've got this issue to deal with then, which isn't too severe because we probably wouldn't want the table to be more than half full anyway. Performance starts to degrade the more full the table gets. We're just saying with quadratic probing, you don't have the option of having a table 70% full. You're going to have to, increase the table size once it's half full, because if you let a quadratic probing table get more than half full, you get some nasty effects. The other downside to quadratic probing was also a downside to linear probing that just didn't happen to matter. We get something known as secondary clustering. And the idea of secondary clustering is one of saying, say I'm hashing 2, I get 1, 2, 3, or 2, 3, 6, 11, 18, 27. That's my table. In other words, values with same initial location have same probing sequence. Anything that hashes to 2 is going to have a second attempt of 3, a third attempt of 6, a fourth attempt of 11, a fifth attempt of 18, and so on. And you might say to yourself, well, that's an inherent property of probing. We said you have your initial location plus your offset. So anything that has the same initial location and the same offset, because everything is using quadratic probing, the offsets will be 0, 1, 4, 9, 16, 25. Anything with the same initial location is going to have the same value for initial location plus 0, the same value for initial location plus 1, the same value for initial location plus 2, the same value for initial location plus 3, and so on. So as far as how we've defined probing so far, this is inherent in that idea. But it is something that we would perhaps like to change. This was the case for linear probing as well. Anything that hashed to 2 at linear probing was going to have a second value of 3, a third attempt of 4, a fourth probe of 5, and so on. The fact that these are spaced out more in the table still means that all the things that hash to 2 are going to cluster together. Just like in linear probing, if all we ever did was insert things that hash to 2, they're going to all cluster together. Likewise with quadratic probing, if all we do is insert things that hash to 2, they still all, in a sense, cluster together. Because if I want to insert the 6th value of the hash to 2, I'm going to collide with the 1st, 2nd, 3rd, 4th, and 5th items that hash to 2. Now, we don't expect that many items that hash to 2, but anyway, we do have this effect of items that start at the same place will collide with each other. You know, any item you insert that hashes to a place is guaranteed to collide with everything else that hashed to that place initially. And what might be kind of neat would be to say 2 different items hash to 2, but for one of them, 3 is the next cell we try, and for one of them, 19 is the next cell we try. If we had 2 items, one of them had a sequence of 2, 3, and then whatever else, one of them had items 2, 19, whatever else. Then if I had already inserted something else, let's say this was, let me do it this way, 237, just however large this table is. If those are 3 different probing sequences, the start of 3 different probing sequences for 3 values, with linear or quadratic probing, I'd have 1 probing sequence, and I'd say the first item goes into cell 2, the second item collides with cell 2, but goes to cell 3, and the third item collides with cell 2 and cell 3 and goes to whatever the next value in the sequence is. If 3 values that hash to 2 have 3 entirely different probing sequences, I can then say the first value goes to 2, the second value collides with 2 and goes to 19, the third value collides with 2 but doesn't collide with 19 because its second value in its probing sequence is entirely different than 3 or 19. So there's no way, we're not going to say, well, it collides with 2 and with 3 or collides with 2 and with 19. What we'd be saying here is any values that hash to 2 end up trying different places for the second location, which means we're going to reduce the number of collisions, because the third value that hashes to 2 will, of course, still collide with the first one, but won't collide with the second one. And the fourth value that hashes to 2 won't collide with, it will collide with the first value at cell 2, but won't collide with the second or third values that hash to 2. Well, that will happen here. When we insert the fourth value, it'll collide with what was put into 2, and it'll collide with what was put into 3, and with what was put into cell 6, and then we'll finally settle into cell 11. Here we'll say the stuff that would, this fourth value will collide with what it went to 2, but it won't collide with the second value we tried to insert because that went to 19 for a second try. It won't collide with the third value we tried to insert because it went, that third value went to 37 for its second try. The value we insert can go collide, do 1 collision, and then go straight to 22. And so the question is, how can we set this up? How can we get it so that the values we have, even if they start at the same location, have different probing sequences? And the answer is, the way we'll set this up, and we'll look at more details tomorrow, but I'm at least going to leave the lecture with this answer. The answer is going to be known as double hashing. And what we're going to do is expand our probing, make it a little more general. We say here, our sort of big probing function here, h of x comma I, we said it was equal to h of x. Our probing function now is going to be a function of I and x. And we say, for linear probing, f of I comma x equals I. We ignore x entirely. And for quadratic probing, we say f of I comma x equals I squared. Once again, we ignore x entirely. So all we've changed here is we now have the probing function will depend not just on how many probes you've done, but will depend on x as well. And our linear probing didn't care about x at all. The probing function was entirely dependent on how many probes you've done. For quadratic probing, likewise, the probing was entirely dependent on how many probes we've done, and we ignored x entirely. For double hashing, what we will say here is f of I comma x will be equal to I times h2 of x, where h2 is some other hash function on x. But as a result, what we'll end up with here is h of x plus 0 times h2 of x, which of course is going to be equal to h of x plus 0, which is what we want. And if that's a collision, we will try h of x plus 1 times h2 of x. If that's a collision, we will try h of x plus 2 times h2 of x. If that's a collision, we will try h of x plus 3 times h2 of x. We'll have to know what this h2 of x is, and we'll go over an example at the start of the next lecture, because we're running out of time here. But the idea here will be this will be our probing sequence. We generate probing sequence values by saying we have here an h of x. Initially, it's just the actual starting location, h of x. Then, whatever h2 of x is, essentially it's sort of an offset of its own, and we'll have multiples of h2 of x. So if the initial hash function, we hash on 16, that brings us to cell 2, as we've been doing. And let's say h2 of x, whatever the function h2 is, h2 of x happens to be 4. Then what we'd say here is we would try 2 plus 0 times 4, 2 plus 1 times 4, 2 plus 2 times 4, 2 plus 3 times 4, and so on, increasing multiples of 4 because h2 of x was 4. So in that way, what we can say is values that can have the same initial location, such as 9, 16, 2, 30, 37, all hashing to 2, could all have different values for h2 of x. And if they all have different values for h2 of x, then the sequences you'll get will be different. The numbers I get if h2 of x is 4, the resultant numbers I get will be different than if h2 of x is 3, will be different than if h2 of x is 5. So now I can have a number of values with the same initial location have different probing sequences because the offsets I'm adding to the initial location are different depending on what our x is. And so what we're doing now is this is the real formula we want for our probing. This is the most general version, or the more general version. And we're just saying then for the earlier probings we looked at, we're ignoring the x parameter entirely in the probing function. For double hashing, we'll actually use it. We'll have the probing function will be a function of I and x. Specifically, it'll be I times the result of some new function on x. We will look at an example, start next time with an example of all this. So we'll go over double hashing next time. And we will also talk about rehashing, which is kind of the mechanics of increasing the table size. And then we will start extendable hashing. That's it for now. So we'll pick up here and then start of the next lecture and talk a little bit about double hashing. See you then.